talk about my results or conclusion as just read. So let me tell you first what the hygrocins are. Hygrocins A and B are like antibacterial activity, but before going into that, I can say hygrocin A and B are like similar, and from there if we look at it, we decide we can make the other hygrocins too, which are like A, C, D, E, F. And hygrocins belong to class of enzymycin. And why they belong to enzymycin? Because they look like basket, and from the basket, if you look at it, you can have like a basket handle. You can just grab these molecules. And why are we talking about enzymycin? Because they, as they say, they are antibiotics. And why we need antibiotics? Because the bugs, these bugs keep evolving there, and for those bugs we need new drugs. And how the drugs work, or the bugs work, the resistance against is just they have this kind of transporter. They just grab the transporter antibacterial and just flux throw it outside the membrane or cell. And this slide just kind of explain how the flux works. They just gene the enzyme. They just gene the whole thing, so it does not, the antibacterial drug does not work. And after that, this is which is a big problem, because the drug antibacterial keeps evolving, and therefore pharmaceutical companies are not making a lot of money, because if there is no drug working, nobody will buy it. And antibacterial need is going up, but the production is going down. As a result, we have less and less antibacterial drug in the market. And as you can see, from 2008 to 2012, we have FDA has approved only 2 more antibacterial drugs, which are telemedicine and ceftriaxone. As a result, as you can see, we can be back to pre-age antibacterial. On the only difference will be bodies will be on the automatic vehicle instead of horses or those things. And where do the new drugs normally come from? From nature, natural products, because they are macrocycles. And this just show the holy grail, macromycin, retromycin, and erythromycin, because they are macrocycles. And why the macrocycles are good? Because they just macrocycles, natural products are macrocycles, because they are not too big, not too small. If they are molecules are too small, they cannot do the protein interaction. But the macrocycles can do it. Therefore, coming back to my original talk, hygrocins, I'm not going to spend a lot of time on this because I have explained it already. And therefore, in this slide, this just slide just shows the biomimetic approach, which my other team members tried it before I started doing research, but I mostly work on non-biomimetic approach. Therefore, I will just go to non-biomimetic approach. And this slide shows the retrosynthesis of hygrocins. And in this slide, you can see hygrocins are macrocycles, macromolecules, and you can synthesize the whole macromolecule. Therefore, we decided to divide into 3 parts, which are aromatic, the acid fragment, and cell chain. And I will mostly talk about aromatic core, but my other team member, my colleague Diene, formulation, and we used the dimethyl sulfate, and we did the anion formulation at the end, and we made the OME enol formation. And after making the N, we did, we already had the other ring B, but we just needed to make it the O, the ketone or oxygen. So we did just use the beta. And we had like acetyl on the end. So we did the Diels-Alder reaction and combined both rings. And as you can see on the side, just you can see like what the beta and P5 looks like, because we tried with both. The P5 is just like a little bit more expensive, but it works a little bit better. But at the end, they both almost give the same results. So it went on with the beta. And on this one, so we did after that we needed the bromine, or like the other ring can come and attach. Therefore, we did the bromination, and at the end we have attached bromine. And on the bottom, you can see the bromine from the X-ray crystal structure. So after this, we like didn't went on with it, because the acetyl is like not really protected group. Therefore, we decided to use another approach, and we use the BOF instead of acetyl, and we did the same reaction, but just use the BOF instead of acetyl. It's just a similar reaction. So after that, it's the same reaction again, just like NMR combination. As you can see, we already had we did the crystal structure, but after that, we just did we used cesium 3 chloride, sodium borohydrate to just make it like more protect the oxygen, those oxygen, so we can like attach those other chiral fragments, and that's from which Jan will talk about. And that's all. So after just to conclude it, I will just talk about. I will just show you my proton NMR, and on this you can see the bark, and over here you can see all those three protons in there, and this will show the 2 OME in here. That's 2. 3
One on the airing.
Yeah.
One on the airing and 2 on the beam.
Yeah. 3. It will show the 3 over here, and just to show it proton NMR too, it just shows those a bark over here too. C3 proton NMR.
Before this is
C3 carbon NMR, C13 NMR, and it just shows NH bar, because it just and just to conclude it, I will just show you the I made that ring. So my other lab partner or associate Gopi made the other fragment, and as you can see, he had the crystal structure. He just did the reactions and grabbed my part, and he attached it. So just to show it, we made this. He published this part. We published this here on the tetrahedron letters, and at the end, over here are proton NMR, and carbon C13 NMR. Just to show it, we actually made that part, and at the end, I will just thank you all, and I will acknowledge thank you all, thank you to all these people and all the colleagues, and at the end, just thank you everyone for paying attention.
You got it. You got to practice more scientifically. Now this is a rough version, right?
Yeah.
You have to define this, and you have to put conclusions. That's missing.